Picture, if you will, the invisible force that literally powers virtually everything in your everyday life. It lights up your home, it powers the device you're using right now, and it runs the hospitals and industries of our entire modern society. But if you were to strip away the wires, the screens, and the bulbs, what are you actually left with? What exactly constitutes electricity? Today, we're going to answer that question, and more importantly, we're going to figure out the fundamental rules that govern exactly how it behaves. Welcome to this explainer. I am so incredibly thrilled you're here. Today, we're taking a sort of building blocks approach to demystifying the physics of electricity. We're going to start incredibly microscopic and build our way all the way up to full working circuits. Okay, let's dive right into this.
Here's our quick roadmap for the explainer. We'll start with flowing charges, then the push, mapping circuits, Ohm's law, resistance factors, and finally resistors in series.
Section 1. Flowing charges, otherwise known as electric current. You know, when you flip a switch to turn on a flashlight, you're creating a continuous, closed path for microscopic particles called electrons to flow through metallic wires. And this rate of flow of electric charge is exactly what we call an electric current. But there's actually a pretty funny historical quirk about this flow. See, when the phenomenon of electricity was first observed, scientists actually didn't even know electrons existed yet. So they kind of had to make a guess. They assumed electricity was the flow of positive charges moving from the positive terminal over to the negative terminal. Today, we call that conventional current. But we know now that actual electrons, which are negative charges, flow in the exact opposite direction, from negative to positive. So, even though the early scientists literally guessed backward, the math somehow still works perfectly, and we still use their conventional direction in circuit diagrams today. It's basically a massive, centuries-old oops that we just decided to keep.
So how do we actually measure this flow? Well, we measure it in a unit called the ampere, which is named after the brilliantly minded French scientist André-Marie Ampère. 1 ampere basically means that 1 coulomb of electric charge is flowing past a specific point every single second. But naturally, that begs the question, what exactly is a coulomb?
6 times 10 to the 18th power. That is roughly 6 quintillion. No, really. When we talk about 1 coulomb of charge flowing through a wire, we are actually talking about nearly 6 quintillion individual electrons moving past a point. When you realize that just a basic, everyday half-ampere light bulb has 3 quintillion electrons rushing through it every single second, the sheer scale of the microscopic world becomes absolutely mind-blowing.
And that brings us to our very first mathematical building block, I equals Q over T. It is, at its heart, a story of movement. I represents the current, our amperes. Q is that massive quantity of charge, our coulombs. And T is the time in seconds. So the current is really just the total charge divided by the time it took to flow. It's exactly like measuring how many gallons of water are rushing down a river per second.
Moving right along to Section 2, the push, or potential difference. So we know electrons can flow, right? But they won't just move on their own. There's a great quote from our source material that explains it perfectly using a water analogy. Imagine a perfectly horizontal tube filled with water. The water just kind of sits there. But if you connect one end of that tube to a high-pressure water tank way up on a hill, well, the pressure difference absolutely forces the water to flow. For electrons in a wire, gravity doesn't do anything at all. Instead, they need an electric pressure difference along the conductor to move. We call this electric pressure potential difference. And we measure this potential difference in volts, named after the Italian physicist Alessandro Volta. Think of a battery. It uses chemical energy to generate this potential difference across its terminals. The battery basically acts as our high-pressure water tank. It provides that absolutely crucial push. Specifically, 1 volt is the potential difference when exactly 1 joule of work is done or energy expended to move that 1 massive coulomb of charge from one point to another.
Which naturally gives us our next formula, V equals W over Q. Voltage is the work done divided by the charge moved. Now, when you see this formula, don't just see a bunch of letters on a page. Visualize the physical reality. This is literally the battery expending its stored chemical energy to physically push those quintillions of electrons through the wire.
Now for sections 3 and 4, mapping circuits and Ohm's law.
Okay, this is where it gets really cool, because this is where we unite our first 2 building blocks, the flow and the push. Back in 1827, German physicist Georg Simon Ohm discovered something incredibly elegant. He found that if you keep the temperature of a metallic wire exactly the same, the potential difference, the voltage, is directly proportional to the current flowing through it. It's a perfect relationship. If you double the push of the battery, you get exactly double the flow of electrons. If you plot voltage against current on a graph, it forms a perfect, beautiful straight line.
So the absolutely crucial takeaway here is how this gives us arguably the most famous equation in basic electricity. V equals I times R. Voltage equals current multiplied by a constant we call R, or resistance. You see, as electrons rush through a wire, they aren't completely free. They're constantly impeded and slowed down by the attraction of the atoms they literally have to navigate through. This property of a conductor to resist the flow of charges is its resistance, and we measure it in ohms.
Which leads us to Section 5, resistance factors. Basically, what actually slows the flow down?
Why are some wires great conductors while others act like giant electrical roadblocks? Well, there are exactly 3 physical traits that dictate this. First up, the length of the conductor. If you double the length of a wire, the electrons have twice as far to travel through that atomic obstacle course, so logically, the resistance doubles. Second, the area of cross-section, or basically the thickness. If you make a wire thicker, it's kind of like adding extra lanes to a busy highway. It offers a much easier path, so the resistance actually goes down. And third, the nature of the material itself. Different elements just simply have different internal atomic structures.
And the beautiful thing is, we can tie all 3 of these traits into one brilliant formula. Resistance equals rho times length divided by area. That funky little symbol rho stands for electrical resistivity. Resistivity is a fundamental characteristic property of every single material in the known universe. It's essentially the nature of the material translated into a hard mathematical number. Let's look at some real-world data to see the massive scale of resistivity we're talking about here. Silver, for example, is an excellent conductor. Its resistivity is extraordinarily low, about 1.6 times 10 to the negative 8th power. Electrons flow through it with immense ease. Then consider an alloy like nichrome, which has a moderately higher resistivity. But then think about a true insulator like glass. Its resistivity is 10 to the 10th all the way up to 10 to the 14th power. It is exponentially harder for electrons to push through glass than silver. The scale here is absolutely staggering.
And this beautifully explains an everyday piece of trivia. Have you ever wondered why the glowing red heating coils inside your kitchen toaster or your electric iron are made of alloys instead of pure metals? Well, applying our newfound physics knowledge, alloys generally have a much higher resistivity than pure metals, so they resist the current and generate a ton of heat. Plus, they have the chemical advantage of not oxidizing or burning away when they get glowing hot. It's literally physics at breakfast.
Finally, we arrive at Section 6, resistors in series. This is where we combine the blocks. Up until now, we've really only looked at single components, but what actually happens when we chain multiple resistors together end-to-end in a single closed loop? Well, when components are chained in series like this, the exact same current flows through all of them, but the total push from the battery has to be divided up to get the electrons through each separate obstacle. So the total potential difference, the total voltage from the battery, is equal to the sum of the voltage drops across each individual resistor. V equals V1 plus V2 plus V3. The battery's energy is perfectly distributed across the entire chain of resistance. So let's take a step back and really look at what we've built here today. We've taken quintillions of completely invisible electrons, given them a specific mathematical push, mapped their flow, and learned to control them using the physical properties of the everyday materials around us. It is just an incredibly beautiful logical system. But it leaves us with a totally thrilling question. If we can manipulate voltage, current, and resistance to so powerfully shape the physical world right now, what entirely new combinations of these basic building blocks will power our future? Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.